So in yesterday's class we finished up with 2 ports. I'll quickly review it before we move on to nonlinear circuits. So the basic idea was reciprocity basically relates the excitation for a linear 2-port, okay, for a linear 2-port made of resistors as what we saw in class. If you excite one port and look at the response at the second port, okay, and if you get a certain response, and if you look at the reverse, if you excite the second port and look at the response of the first port, those two are related in some way, right? Depending on what you excite with and what response you see, you can get different forms of reciprocity, and these will be expressed in different ways using the several 2-port parameters that we have studied. In the simplest case, for example, if you were applying a voltage and looking at the current, okay, you can represent it in terms of the Y parameters. Y21 will be equal to Y12. Okay, you can get different relations between the other 2-port parameters also. And we are specifically going to use this because we want to find out what will happen if you take up 2-port, take a particular element in the 2-port. Okay, let's say in this case it's some resistor R, and what happens to the input current I1 if you change R to R plus delta R. So you're basically finding out the sensitivity of I1 to R. That is pretty much what you're doing. Okay, and we happen to use this particular result of reciprocity. Okay, before that what you do is you replace the delta R, the extra resistance, using substitution theorem. You replace it using the voltage source equal to IR plus delta R times delta R, which is the same as, which is almost equal to IR times delta R. Okay, and now you have a linear 2-port which is excited by 2 sources, okay, one at each port, and therefore you can use superposition and reciprocity to determine what this delta I1 would be. And we found out that delta I1 was minus IR squared by Vs times delta R. The basic idea is not to memorize this result, you don't need to know this by heart, but the idea is to understand how it came about to be, right? So the idea is how you use reciprocity and substitution to arrive at this result. Okay, this particular result is called compensation theorem. Next we looked at what 2-port parameters would be most appropriate to represent different kinds of ideal controlled sources, and if you do not want to handle infinite quantities, you will find that only one set of parameters will easily describe each ideal controlled source. Okay, so in the case of the ideal voltage controlled voltage source, you will find that G parameters are the natural ways to represent them, and for each ideal control source you can come up with one of these. Any questions so far? Now we will just go through what we did in the last couple of minutes again. In our next topic of interest, are what are called nonlinear circuits, and we are going to spend maybe a couple of classes on nonlinear circuits. The basic difference between nonlinear circuits and linear circuits obviously is that the relationship between the currents and voltages in a nonlinear circuit, okay, is nonlinear, right? But that leads to so many ramifications because all the theorems, all the networks, what we have been considering so far are for linear elements and linear networks. Okay, so we need to figure out at least how to handle these kinds of nonlinear circuits in some situations. How do we make it easier to analyze nonlinear circuits in some situations? Now the point is, we will give you an I will give you an introduction in this course, in the next course on analog circuits, you will be dealing pretty much only with nonlinear circuits. Okay? Because every new element that you will learn in that course, and you will learn to use those elements, okay, they will be nonlinear, but we are going to try to figure out how to analyze them in an easier fashion. Okay, so we'll take the simplest possible case. We'll just take a single loop, 2 elements, 1 voltage source, some Vs, some R1 and some Z, which has a relationship I equals f of V. Okay. So if you try to write down the relationship describing these two elements, describing the system, okay, the first one is KVL around the loop. So I equals Vs minus V by R1. That uses KVL to describe the system. The second relationship is the elemental relationship, I equals f of V. Okay, so we want to somehow use these two to solve the system. How do you think you will do this? Unfortunately, there is no shortcut. Okay, unfortunately there is no shortcut. You have to solve the nonlinear equation that you get. Okay, so any network which has nonlinear elements, you will have to use the nonlinear elemental relationships to find out the voltages and currents in the network. Okay, the good thing is many of these nonlinear relationships are simple functions that we already know, right, such as exponential. One of the first elements that we are going to look at has an exponential relationship. Okay, it is not some arbitrary polynomial, okay, with some arbitrary degree. The most commonly used elements have well-known functions. The first element that we are going to look at is what is called a diode. Okay, so a diode, the symbol of a diode is this. Okay, so this is the what is called the anode. This is what is called the cathode. The voltage is in this direction, reference voltage. The reference current is in this direction. Okay, this is the first, and in this course the only nonlinear element that we'll study in class. If you look at the tutorial number 5, which is going to be posted later today, you will find that there are a couple of more nonlinear elements that you will be introduced to. You will never use it in this course. Obviously, it will not appear in the exam and so on. Okay, those advanced elements you will study in the analog circuits course. So we will consider the case of a diode. Okay, and the diode happens to be a passive element. Okay, it does not generate power. Okay, it only dissipates power, and of course it is non-linear. The current voltage relationship for a diode, okay, is in the following manner. It is some Is okay times, it is the current is some Is times exponential V by Vt minus 1. Okay, this is the equation describing the voltage current relationship for a diode. Suppose I want to understand what would happen if I put the diode in a circuit. One of the easiest ways to understand this is using first of all you need to plot out what these characteristics look like. Okay, for any element it always helps to plot out the characteristics and see what they look like. Okay, because number one, it will help you to understand what happens when different voltages are applied to the diode, and you want to find out what the current is, and vice versa. That's number one. But more importantly, as we'll see in today's class, it can also help you to solve some very simple circuits, get some intuition on what happens inside these networks. So let us plot out the characteristics of the diode. So this is I times V, I versus V. So what happens when V is very large and negative? So let me write down the relationship here again so that So what happens when V is very large and negative? I happens to be equal to minus Is. Okay? And for a typical diode, this value of Is is very, very small. So Is may be of the, let us say, extremely small. Okay, maybe 10 power minus 12, 10 power minus 15 amperes, which obviously is very much smaller than the kinds of numbers we have been looking at so far. And it's usually much smaller than the numbers you will be dealing in a majority of cases. Okay? So when V is very small and negative, it is equal to minus Is, and it remains minus Is for pretty much all large and negative values of V. Right? Whether you take, what really matters is the ratio of V by Vt. Now the next question is, what is Vt? Right? Vt is Kt by Q. Okay? See, we are writing down the elemental relationship for a diode. Okay? And as it so happens, it depends on certain parameters. Just like if you take a resistor, a linear element, what is the parameter that describes its operation? The value of the resistor, R. Right? V equals IR. R describes the relationship. For a diode, its voltage current relationship is described by Is and Vt. Okay? Vt is nothing but Kt by Q. So I'll write down the definitions of Is here. Is is what is called the saturation current. Okay, and Vt is what is called the thermal voltage. Okay, typically Is is extremely small, Vt is Kt by Q. What is K? Boltzmann's constant. What is T? The absolute temperature. In Kelvin. And Q is the electronic charge. Okay? What is the value of Boltzmann's constant? 1.38 into 10 power minus 23 what? What are the units of Boltzmann's constant? What is that? Joules per? Joules per? Molecule? No. Joules per Kelvin. What is Kt? You must have seen this number Kt before. What is Kt? Kt is some form of energy, right? Okay. So K should be some joules per Kelvin. Okay. K is absolute temperature. Typically it's in Kelvin. We will assume in a majority of cases the circuits, these diode is operating at room temperature. Let's say around 300 Kelvin because it's a nice round number. Okay. Electronic charge is, I hope everybody remembers this, it's 1.6 into 10 power minus 19 coulombs. Okay. And Kt by Q has the units of volts. Okay. At room temperature, let's say 300 Kelvin. Vt is approximately 25.9 millivolts. Okay. Now note that we are now talking about nonlinear circuits. Okay. You will need typically you would go to a simulator to get very accurate results. So an approximate hand calculation is good enough in many cases, and therefore we will often say this is either 25 millivolts or 26 millivolts depending on the situation. You will usually be given what this value is. Okay, you will usually be given what this value is, whether it's 25, 25.9 or 26. In any case, it will be obvious from the situation. Okay, you can use any of these, you will get an approximate answer that is good enough in this course. Okay. Now let us go back to the plot. So now, as long as V by Vt is very, very large, the current will remain at minus Is. Okay. Then what happens when V is 0? I is also 0. Okay. So this curve will do something like this. It will do this. Then what happens when V is positive and greater than Vt? Of course, it will take some kind of exponential behavior. Okay, it will take some kind of exponential behavior. And in cases where V by Vt is much larger than 1, okay, what can you approximate this relationship by? Just a simple exponential. If V by Vt was much larger than 1, exponential V by Vt is also much larger than 1, right? As soon as V by Vt goes larger than maybe 4 or 5, okay, you automatically have the first term, this term being much larger than 1. Okay, so in many cases, okay, you will find an approximation for this relationship, maybe in this region. You could say it's approximately okay. Similarly, in this region, these are all common sense approximations, because in any case you are going to be doing a hand calculation which is necessarily going to have some inaccuracy. Okay. Any questions so far? So for various reasons, this portion of the characteristic is called a forward bias, okay, and this portion of the characteristic is called a reverse bias. You will see why it is called a forward bias and a reverse bias, okay, maybe later on in the next course. We won't see it in this course, but this is just for your information. Now, the minute you know this Vt and Is, you can actually write down for different values of V what I would be, or vice versa, right? You can do either of these, and the actual values don't matter, but you can tabulate these numbers. Now suppose I go back to my original circuit, and I put in this diode, okay, and I want to find out what the network state is, as in I want to know what I is, I want to know what the voltage across R1 is, I want to know what the voltage across the diode is, and so on. How would you solve this? As we wrote down earlier, you have two relationships. I equals f of v and I equals Vs minus V by R1. These are the two relationships that describe the system, voltages and currents in the system. How would you solve this? Of course, one way is to, how did you solve it in the case of the resistor? You substituted, you took one relationship, put it into the other one, and then solved it, right, in the easiest case. Now you can start off like that here too. You can take the first equation and plug it into the second one, okay, and you can get a nonlinear equation. And how would you solve a nonlinear equation? Have any of you ever solved nonlinear equations so far? No? I assume you have solved quadratic equations, which are by definition nonlinear, right? Okay. Have you ever solved arbitrary nonlinear equations? If I gave you a cubic, okay, would you be able to solve it? How would you solve it? Huh? What is that? Newton-Raphson method. Has anybody heard of Newton-Raphson method? Oh, you have. Some of you have, some of you haven't. Okay, so the basic idea is, if you want to solve some of these nonlinear equations, there are certain numerical techniques that are available. Newton-Raphson is one of them. Okay, it so happens that Newton-Raphson is one of them, and you can basically use them to solve it. Many of them use some modified form of successive iteration. Okay, and in many cases, just simple successive iteration might get you to the answer. Obviously, there are issues with just blindly using successive iteration. We won't go into that here, but there are ways to solve this. Okay, there are ways to solve this, and typically simulators would be using one of these numerical methods to get to the final answer. Okay, especially when f of v may be any arbitrary function. Okay, especially if it's an exponential, it's not so easy to solve it in a straightforward manner. The other way to solve it is using graphical methods. Okay, how would you solve something like this using graphical methods? Suppose I gave you the system and I said solve it graphically. How would you do it? So I have these two relationships. Okay, I would plot. One of them is I equals Vs minus V by R1. The other is I equals f of V. If I plot each of these on the same set of axes, on the same graph, how do I find out the solution? The intersection point of these two curves will give me the solution, right? So let us do that here. So in our specific case, this is our nonlinear function. Okay, I need to plot both of these on the same set of axes. So let me call this A, let me call this B. A looks something like this. Okay. What does B look like? What kind of relationship is B? It's a straight line with a negative slope. Okay, what is the value of the slope? Minus 1 by R1. So I'll draw it something like this. Okay, this is B. The slope is minus 1 by R1. What is the y-intercept? Vs by R1. What is the x-intercept? Vs. Okay. What is the steady state of this? This is the steady state. I'll denote it by V0 and I0. All good so far? Any questions? Okay, so now using this graphical method I have actually solved this system. Now suppose I told you that Vs is no longer Vs but some Vs prime, and I'll write it as some Vs plus delta V. Vs has now changed. Okay, how would I find out the new solution? Okay, let us take the analogous case for, first let us take the analogous case for linear network. Suppose I had a resistor here, I had Vs and I found out V0, I0, right? Now I am telling you this has become Vs plus delta Vs. How would you solve this problem? If I told you I have a network, I know the solution for Vs when a source Vs is applied to the network. I want to find out what happens when Vs plus delta Vs is applied. How would you do it? You can do it in many ways. Of course, you can solve the complete network, okay, with Vs plus delta Vs, or you could apply superposition and say I apply only delta Vs. Okay, so I can split this up into two parts, and I can say one part has only Vs, the second part has only delta Vs, and I then add the two results to get me the final solution, right? Now can I do that in this case? So this is superposition. Can I do that in this case? Why not? Because the circuit is nonlinear, because there is a nonlinear element inside the network and I can no longer use superposition. Okay, that's number one. Is that clear? So you cannot say what happens when you add Vs plus delta V. Okay, suppose I had Vs was initially 5 volts, and if I apply 10 volts, okay, I cannot say it is 5 plus 5, right? I cannot say it is just double the original voltage, because very clearly the relationship is non-linear. Now let us consider a very special case when delta V is very small. Okay, we are going to consider a very special case when delta V is extremely small. Can you think of some way to do this? First of all, what will happen to the, let's say Vs became Vs plus delta V. Let us see what will happen to the two curves. Okay, the curve in blue, the diode characteristic, will that change? No, because it does not depend on Vs. However, the curve B will shift slightly. Okay, it will shift in this direction. Okay, that will be the new curve. The new intercept is Vs plus delta Vs by Vs plus delta V by R. This new x-intercept is Vs plus delta V. I'll call that delta Vs. Sorry for the mess up. It's Vs plus delta Vs. Okay, and this new intersection point will give me the new V and I, that is the state of the circuit. Okay, is that clear so far? Any questions? Okay, now suppose I had just told you are applying Vs plus delta Vs, and let us say you did not have the option of doing it graphically. What would you do? Because the graphical solution is typically not going to be very accurate. It's very good for getting intuition, but if you're going to solve it using a CAD tool, a simulator, you probably won't go the graphical method. You would use some kind of numerical method, right? Some kind of analytical method. So what would you do if I just told you, you had Vs plus delta Vs? Okay, let us take a step back. How would you have found out I0 and V0? By using some analytical method. Okay, you would have found out V0, I0 by solving the nonlinear equation. How would you find out this new value, V0 prime and I0 prime? You would again have to solve the nonlinear equation again. Okay, there is no other way. Okay, if you are planning, if you have solve it, okay, if you were to solve for the new curve, okay, and if you just brute force it, you would just have to solve the nonlinear equation again and find out this new V0 prime, I0 prime using numerical methods. Now the point is, we want to find out if there is an easier way to arrive at this V0 prime, I0 prime, okay, without going through the solution of the nonlinear equation again. Okay, so any ideas on how you could do this? Sorry? Taylor series expansion. That's a good solution. How many of you know what Taylor series is? Okay, so almost all of you. So what is the basic concept of a Taylor series? You expand the polynomial. In what way? Around a particular point. Okay. Okay, I'll explain it graphically. I want all of you to go back and read again what Taylor series is. Okay, but the basic idea is very simple. You are trying to expand the, so if I have a, I'll just draw this half of the curve. I have some nonlinear relationship, okay, and around a particular point, let us say I0 comma V0, sorry, V0 comma I0, I can expand the expression, okay, using the derivatives, right, the first derivative, second derivative and so on of the function describing the relationship f, and I can find it out for other values, right? I can find out other values using just the derivatives and one particular set of values V0 comma I0. That is the basic idea of Taylor series. Now if I tell you that the change is, so once I know V0 I0, I can actually find out any other point on the curve using the Taylor series. Now if I tell you that the change from V0 I0 to the new point is very small, so in other words, let us go back. This was Vs, this became delta Vs, and I became I plus delta I, V became V plus delta V, and I told you that delta V, delta I and delta Vs are all extremely small. Okay, what could you say about the Taylor series expansion around V0 I0? What is that? You can approximate it by considering only the first derivative. Okay, what is the first derivative? you are basically linearizing the curve. You are looking at the tangent to that point of consideration. Do you see that? The Taylor series expansion gives you as long as you consider an arbitrary number of terms, okay, you can get any new point on the curve. However, if you say that the change is very small, you can approximate it using only the first derivative, which happens to be the tangent. So in other words, what I am saying is, you take any nonlinear curve, you keep zooming in till you reach a point, till you reach a scale where the curve can be approximated by a straight line. That is what we are saying here. Is that clear? I consider a small enough delta V and delta I and so on such that the curve can be approximated by a straight line. Okay? Now how do you ensure that you have considered a small enough delta V and delta I? Well, you will have to assume that it is satisfied, and you will have to go back and check to make sure that, ensure that it is satisfied. Now let us go back to this curve. I want to draw it in a slightly bigger manner. This is my diode characteristics. This is my original resistance, okay, and this is V0, this is I0, and now this is changed, this Vs intercept, okay, so this used to be Vs and Vs by R1, that is now changed to Vs plus delta Vs and Vs plus delta Vs by R1, and I think I used, I'll expand it out slightly, okay. I'll expand it out slightly. Okay, this is Vs plus delta Vs. Okay, and I'll also show the tangent here. Okay, now how do I analyze what will happen? So one way to do this, okay, what I'm going to do, initially this was the origin. Now what I'm going to do, I'm going to move the origin to this. Okay, I'm going to move the origin to V0 comma I0. Okay, and you'll see why I'm doing this. The minute I move the origin to V0 comma I0, what happens to this extra terms? These extra terms, what is this? So, sorry. What will happen to these new curves now? Sorry, let me look at what colors I've used. Okay. Okay, good. What is this? What is this line here in whatever color that is, purple or something? What does that represent? The characteristics of the diode. Okay, this represents the characteristics of the diode. Okay, now what do I do here? I need to draw the characteristics of the resistor. For that I believe I have used this color. Yes. Okay. what is this value here now on this new I prime V prime axis? What is this intercept now? This is delta Vs. What is this intercept? Delta Vs by R1. Okay. Now, is there any nonlinear curve in this particular graph? There is none. I have replaced the diode by a linear characteristic. I have replaced the resistance by a linear characteristic. In fact, if I had given you a network, so let us say this was V1, R1, R2, you could have solved this graphically. It would have given you the same set of or same type of characteristics. You would have drawn the characteristic for the mesh equation here. Okay, that would have given you something like this. You would have drawn out the elemental relationship for the resistance. That would have given you something like this. Is that clear? Basically what we are doing is, the minute you move the axis to V0, I0, okay, what you are saying is, the diode now looks like a resistor. You have a linear characteristic which is passing through the origin, because this is the tangent to the curve at that point, so it will pass through the origin. Is that clear? So this V0, I0, okay, so V0, I0 is also called the operating point. Okay, V0, I0 is called the operating point of the diode, and delta Vs is called an increment or an incremental voltage. Okay, now this kind of picture where you have drawn I prime versus V prime, you are only linearizing the diode characteristic and you are considering only delta Vs and so on. This is called an incremental picture. Okay, because you have removed out the original value Vs and so on, Vs and V. You are now looking only at delta Vs and delta V and delta I. Is that clear? So in our specific case, so this is Vs, okay, but specifically this is delta Vs now. I'll call this Rd, where Rd represents the incremental resistance of the diode. Okay. Sometimes people also call it the dynamic resistance of the diode. Okay. Now does it matter that we have considered a diode here? It really does not. You could have taken any non-linear two-terminal element and replaced it by a resistance based on a linearization using the first term of the Taylor series expansion for that function. Okay. What is this Rd here? So now what will be this Rd? What will be the slope of this line? The slope of this line for any resistor, what is it? It's 1 over R. Okay, you are drawing I versus V. The slope of this is 1 over R. So what is Rd? 1 over F prime of V. Okay, the resistance Rd is 1 over F dash of V. Is that clear? It's the first 1 over the first derivative of the function F of V, calculated at V0. Okay, that is very important, because if you change V0, the dynamic resistance will change. If you had taken the tangent at a different point, very clearly, if you had taken the tangent somewhere here, right, the slope of the tangent changes, the dynamic resistance of the diode will change. Okay, so what is the procedure? If you are given a circuit like this and are asked to calculate what happens when you apply an increment, what you do is, you first calculate the operating point, and there is no other way to calculate the operating point but to use the nonlinear equation describing the diode. However, once you have done this for V0, I0, around this V0, I0, for any increment which is not too large, you can linearize the circuit and find out what happens. I hope that is very clear, and I hope you see why this method could be very powerful. Okay, because if I told you, let us say I applied 5 volts, okay, and I got some current and I got some voltage across the diode, okay, and I made that 5.01, I can find out what happens using just usual linear approximations, and everything that goes with linear approximations will be perfectly valid. Superposition will be valid for these incremental delta V's. Okay, so you can see why this could be extremely powerful. Now you will be using this in a very large way in the analog circuits course. Okay, you will be using this in an extremely, very often in the analog circuits course. Now the diode happens to be a 2-terminal element that is nonlinear. You can also do the same thing for 2-port elements, that is 4-terminal or 3-terminal elements. Okay, we will do that next class. We will see how this can be extended to more complicated elements. Okay, we'll stop here.